Welcome to this NPTEL lectures on robotics, basic and advanced concepts. In the last lecture, we looked at parallel manipulator Jacobian matrix. Okay, in this lecture, we look at the singularities in serial and parallel manipulators. Just a review of the serial manipulator velocity kinematics. So the direct velocity kinematics is given by, on the left hand side of this equation, we have linear and angular velocity of the tool coordinate system, which is related to the joint rates theta dot by this Jacobian matrix. So 0 tool Jacobian into theta dot will give the linear and angular velocity of the end effector or the tool coordinate system. So for known theta and theta dot, linear and angular velocity of the end effector can be obtained from the above equation. And this 0 v tool always exists. Okay, so remember, this is not a proper vector. This is not a proper matrix because part of the matrix contains meters per second or meters. Okay, and the bottom half, the angular velocity, is in radians per second. So the inverse velocity kinematics exists if this Jacobian matrix is square and the inverse of the Jacobian matrix exists. So given linear and angular velocity of the tool coordinate system, if the inverse of the Jacobian matrix exists, we can multiply inverse into v tool and we'll get theta dot. Okay, so the joint rates, in summary, can be obtained when the Jacobian matrix is square and the determinant of this Jacobian matrix is not 0. When the determinant of the Jacobian matrix is 0, what happens is there is a loss of rank of this Jacobian matrix. Okay, this is from linear algebra, straightforward linear algebra. If you have a matrix A, n by n matrix, and the determinant of that matrix is 0, then the rank of that matrix is less than n. In robotics, these are called singular configuration. Okay, so at a singular configuration, theta dot cannot be obtained for a given linear and angular velocity. So, example, for a planar 2R manipulator, x dot y dot can be written in terms of theta 1 dot and theta 2 dot. Theta 1 dot and theta 2 dot are the joint rates in terms of sine and cosine of the angles, and L1, L2, and so on. Okay, this we have seen earlier also. So the Jacobian matrix in this case is the quantity in the square bracket. So the first element is minus L1 S1 minus L2 S12. The second element is minus L2 S12. The second row first element is L1 C1 plus L2 C12, and 2 element is L2 C12. Okay, C12 stands for cosine of theta 1 plus theta 2. S12 stands for sine of theta 1 plus theta 2, and S1 and S2 and so on are the sine and cosine of the angles. So the determinant of this can be easily computed, this into this minus this into this, and it turns out that the determinant is 0 when sine theta 2 is 0. Okay, the determinant will simplify to simple sine theta 2, and this is 0 when theta 2 is 0 or pi. Okay, so basically the determinant of the Jacobian is 0 when theta 2 is 0 and pi. And what is 0 and pi? If you go back and try to visualize what the planar 2R robot was doing, the second joint is 0, so that means it is completely stretched out, second link, or it is completely folded on top of the first link. Okay, so let's draw these two configurations. So we have a 2R robot, which is L1 and L2. So if it is completely stretched out, the point is on the boundary. Okay, remember for the planar robot, the maximum reach is at radius L1 plus L2, and the minimum it can come to near to the origin is L1 minus L2. Okay, so for theta 2 as 0 and pi, the end effector is completely stretched out or completely folded in. And as you can see that the velocity vector of this end effector can be only tangent to this outer circle or tangent to this inner circle. Okay, so it can only move perpendicular to the line connecting O1, O2 and extended both directions. Okay, so the end effector velocity component cannot be along the second link. Okay, it must be perpendicular to the second link. So as a result, as you can clearly see, there is an instantaneous loss of 1 degree of freedom. The 2R robot has 2 degrees of freedom, but the end of the robot can only move tangent to the circle, perpendicular to the links, okay, line connecting the two origins. So this is happening instantaneously, only when theta 2 is 0 or pi. Okay, when it is pi, you can see again it is tangent to this circle and it is perpendicular to the link. So at theta 2 equals 0 or pi, the velocity ellipse degenerates to a line. Remember, at any other point, I can draw the tip of the velocity vector as theta 1 dot square plus theta 2 dot square is equal to 1. Okay, so it traces an ellipse in the plane. However, when it is completely stretched out or completely folded, it can be only along a line. So the velocity ellipse degenerates to a line. And this is only along the direction of motion, possible direction of motion. For 2R planar example, the Jacobian matrix can also be inverted easily. It's a simple 2 by 2 matrix. And we can write theta 1 dot theta 2 dot is 1 over L1, L2, S2. S2 is sine theta 2. L1 and L2 are the two link lengths. And the elements of the matrix are L2, C12, L2, S12, minus L1, C1, minus L2, C12, minus L1, S1, minus L2, S12 into x dot y dot. So I can find theta 1 dot is something into x dot divided by L1, L2, S2. Okay, so that is the important part. Theta 2 dot is also divided by L1, L2, S2. So when theta 2 tends to 0, which is determinant of the Jacobian going to 0, or pi, S2 will go to 0 and theta 1 dot theta 2 dot tends to infinity. This is also a very important result. So when the tip of the manipulator is very close to the boundary, okay, not at the boundary but close to the boundary, the theta 1 dot theta 2 dot will become very large. Okay, it tends to infinity as it comes close to the boundary. So this knowledge of singularity is very important. Okay, so even when this determinant of the Jacobian is close to 0, the joint velocities tend to become very large for a desired x dot y dot. Okay, and this can cause problems for the controller of the robot. The controller or the motors may not be able to supply the joint rates required. Singularities occur in all Syrian manipulators and not only in planar 2R. So this is a statement and you can verify it and it is well known. Okay. For planar 2R, singularity occurs only at the workspace boundaries. As you can see, it is only theta 2 is 0 or pi, only at the complete outside stretched or completely folded. In other manipulators, for example, in spatial 6 degree of freedom manipulators, it can happen inside the workspace also, at other points also. Okay, so let's review parallel manipulator once more. In parallel manipulator, the equivalent Jacobian can be found and we can use the equivalent Jacobian. Okay, so for parallel manipulators, the linear and angular velocity Jacobians are JV minus JV star K star inverse K, and J omega equivalent is J omega minus J omega star K star inverse K. Okay, so the equivalent Jacobian can be formed by concatenating JV equivalent and J omega equivalent, one on top of the other. Okay, and again, we can see that the determinant of J equivalent equal to 0, the end effector will again lose 1 or more degrees of freedom. Okay, we can also show or see that theta dot will tend to infinity because theta dot will be equal to some matrix divided by the determinant of the Jacobian, equivalent Jacobian. Okay, and Similar to serial robots, at a singularity, velocity ellipse or ellipsoid degenerates. Okay, so in the case of planar 2R, it degenerated from a ellipse to a straight line. Okay, in the case in 3D, we can show that the ellipsoid can degenerate to an ellipse, or the ellipse can degenerate to a straight line. So in addition to loss singularity, where we lose one or more degrees of freedom, in parallel manipulator there exists another kind of singularity, and this is what we will discuss next. This is called gain singularity. Okay, so let's continue. So let's consider theta dot as 0. Okay, the case when theta dot is 0. What is theta dot? These are the actuated joints. So theta dot 0 means the actuated joints are locked. So if you lock all the actuated joints, the mechanism should become a structure, right? Because those are the degrees of freedom. Okay, and then you lock them, and then it should become a structure. Now, loop closure equation, when we took the partial derivatives or derivative with respect to time and rearranged, it could be written as k into theta dot plus k star into phi dot equal to 0. Now for theta dot equal to 0, when the actuated joints are locked, we are left with k star into phi dot equal to 0. Okay, so the first term goes to 0, the second term remains. So from linear algebra, we know that if you have a matrix equation A into x equal to 0, it can have a non-zero x when the determinant of that matrix is 0. So in this case, we can get a non-zero phi dot denoted by phi dot star when the determinant of k star is 0. Okay, so and what is this solution phi dot star? It is nothing but the eigenvector corresponding to the 0 eigenvalue of k star. Okay, so this is well known in linear algebra that Ax equal to 0 has a non-trivial x when determinant of A equal to 0. So for this non-zero phi star dot and theta dot equal to 0, we can substitute back in the expression for the angular velocity of the tool and the linear velocity of the tool, and we are now left with terms containing phi dot star. So it will be j omega star into phi dot star, and linear velocity is jv star into phi dot star. So what do we have? Even with the actuators locked, the linear and angular velocity are not 0, okay, of the tool coordinate system. Okay, so this is an important observation, that the end effector of a parallel manipulator can instantaneously gain one or more degrees of freedom, and this is called as gain singularity. Why is it instantaneous? Because this only happens at the place when this determinant of k star is equal to 0, and determinant of k star is a function of q, so it can happen only at some q. So a geometric picture of a parallel manipulator with gain singularity. Basically, at a non-singular configuration, if theta dot is 0, phi dot will be 0. Okay, so if determinant of k star is not equal to 0, both theta dot and phi dot will be equal to 0, and hence the linear velocity of the tool will be 0. Okay, so at a non-singular configuration, the position velocity ellipsoid is of 0 size. Okay, the velocity vector is 0 magnitude. Or you can think of it as a ellipsoid of 0 size. Okay, at a gain singularity configuration, there is a loss of rank of k star. Okay, so if the rank of k star is m minus 1, okay, normally k is m by m matrix. If the rank is m minus 1, there exists a non-zero eigenvector phi1 dot for the 0 eigenvalue of k star. Okay, so if phi1 dot is an eigenvector, then c1 into phi dot is also an eigenvector with c1 a scaling constant. So for theta dot equal to 0, the linear velocity is now c1 into jv star phi1 dot. Okay, so there can be a motion along this vector jv star into phi1 dot. Okay, so this is an eigenvector, and jv star multiplied by eigenvector will give a certain direction. So what do we have? When determinant of k star is equal to 0, there is a loss of rank to, let's say, m minus 1. Then the zero velocity ellipsoid grows into a line. It can move along this direction jv star phi1 dot. If the rank of matrix K is m minus 2, which means it has fallen by 2, then the linear velocity of the tool can be written as some C1 JV star phi1 dot plus C2 JV star phi2 dot. So there are two eigenvectors corresponding to the two zero eigenvalues of K star, and C1 and C2 are two scaling constants. So for C1 squared plus C2 squared equal to 1, the tip of the velocity vector traces an ellipse. Okay, so C1 and C2 are similar to theta 1 dot and theta 2 dot, and C1 squared plus C2 squared is same as the constraint theta 1 dot squared plus theta 2 dot squared equal to 1, which we used in the planar 2R example. Okay, and exactly the same reasoning as the planar 2R when we discuss the geometric picture of the Jacobian matrix. We can show that the tip of the velocity vector, linear velocity vector, for the parallel robot also lies on an ellipse. Okay, so if the rank of Kc star is m minus 3, then the tip of the velocity vector will lie on an ellipsoid. Okay, how about if it is less than m minus 3? Okay, then and only the linear velocity is of interest, then it is similar to a redundant serial manipulator. So this gain singularity occurs in parallel hybrid manipulators. Okay. In a fully parallel 6-degree of freedom manipulator, what is a fully parallel 6-degree of freedom manipulator? The end effector is directly connected to the base by one actuated joint, okay, as in the Stewart-Gauss platform. Okay. In such fully parallel 6-degree of freedom manipulators, only gain singularity possible. This was shown by Hunt. Okay, we cannot have loss of degrees of freedom because it's a prismatic joint, and at the end only joint limits happen. Okay, there is nothing else happening in the range of motion of the joints. In 6-degree of freedom hybrid parallel manipulator, where it is not fully parallel, in parallel. So for example, the example of 3-degree of freedom hand. Okay, so in each finger there were 3 joints. Okay, it was not directly connected to the gripped object. Both loss and gain of singularity are possible. So the gain singularity is related to the capability of resisting external forces or moments. This we will see in the next lecture. Okay, so at a gain singularity, the manipulator cannot resist even infinitesimally small external forces. There are a large amount of literature on singularity analysis of parallel manipulators. Okay, it's a very, very important topic. We need to know what is happening at the gain singularity, and again from the point of view of control. Okay, it has nothing to do with the joint limits. Okay, it is happening because at some configuration determinant of k star is equal to 0. If you think about it, the determinant of k star is related to the loop closure constraint equations. Okay, and there is something which is happening to the loop closure constraint equation which results in determinant of k star equal to 0. Okay, and if you think a little bit, the rows of k star are not independent anymore, which if you think a little bit more deeply, we can show that the constraint equations are not independent. So we would like to know when the constraint equations are not independent. When you get this additional degree of freedom, what happens to the control of the parallel robot at a gain singularity? Okay, you cannot control it. It has been shown by researchers. So singularity analysis is an active topic of research. Okay, we have also done a lot of work at IISc. So the special link geometry, link lengths and geometry We can also have gain over a finite range of motion. Okay, so this is an example of a 5-bar mechanism. So this is theta 1, theta 2. A 5-bar mechanism has 2 degrees of freedom. Okay, you can show. So there are 1, 2, 3, 4, and 5 joints. Okay, so there is link L1, L2, L3, L4, and one L0. So for a special link length, which is L2 is equal to L3, and this geometry is such that this L1, L4, and L0 form a triangle, and L2 is equal to L3. You can see that these two links can rotate completely, okay, even when theta 1 and theta 2 are locked. So these are typically the actuated joint variables in a 5-bar mechanism. Okay, so if I lock theta 1 and theta 2, this link or this joint angle can rotate freely, and it can rotate over 0 to 2 pi. Okay, so this happens only because of some special link lengths and geometry. So the passive link can show instantaneous and finite dwell. Dwell means it is not moving. So that is also possible. Let's look at the singularities in a 4-bar mechanism. So we have this 4-bar mechanism, link 1, link 2, link 3. Okay. So the determinant of K star for the 4-bar mechanism equal to 0 leads to this equation, which is L2 L3 sine theta 1 plus phi 2 minus phi 1 is equal to 0. So theta 1 plus phi 2 minus phi 1 is equal to 0, which means theta 1 plus phi 2 minus phi 1 is n pi, or phi 3 is 2 pi, because these 4 angles form the inside of a triangle, which means that link 2 and link 3 are parallel. Okay, so this is what determinant of K star equal to 0 mean as far as the geometry of the configuration of the 4-bar mechanism is concerned. So with theta 1 locked, if theta 1 is locked, then this second joint is also locked, right? So O2 is also fixed. But link 2 and link 3 are along a straight line with a joint in between. So if you think about it, this point O3 can instantaneously move perpendicular to this line. Okay, so this point, if you look at it from link 2, lies on a circle. This point, if you look at it from link 3, lies on a circle. So the common tangent to this circle, O3 point, can move instantaneously along in this direction. Okay, so this is the meaning of this instantaneous gain of degree of freedom. So although theta 1 is locked, this joint is locked, this joint is also locked, this point can move instantaneously up and down in this perpendicular to the two links. For 3 degree of freedom 3 RPS manipulator, or a manipulator moving in spatially, okay, the determinant of JV equivalent equal to 0 implies that the linear velocity ellipsoid described by the centroid of the top platform degenerates into an ellipse. Okay, this was worked by one of my students a long time back. These numbers are from that work. So for L1, L2, L3 given by 0.5, 1.0, 1.9710 meters, you can solve the direct kinematics for this 3 RPS parallel manipulator and find that theta 1, theta 2, theta 3 are given by these values: 1.169, 0.478, 2355 radians. And for this combination of actuated and passive joint variables, determinant of JV equivalent is 0. Okay, so the linear velocity at this configuration is shown in the sectional and 3D view next. Okay, so normally we expect a ellipsoid and the sectional views should be ellipses. Okay, we will see later that it is no longer an ellipsoid, an ellipsis. Okay, so this is not a contradiction according to Hunt. Okay, this is a fully in parallel manipulator, According to Hunt, there should not be any loss of degrees of freedom. However, this is not a contradiction because this 3 RPS manipulator is not a 6 degree of freedom manipulator, and only we are interested in the linear velocity of the centroid. Okay, we are not considering both the linear and the angular velocity, and it is not a 6 degree of freedom manipulator. So as I said, we can plot the tip of the linear velocity vector, and it turns out that this is a 3D plot, Vx, Vy, Vz. It lies on an ellipse. Okay. The fact that it is at a singular configuration can be seen in this Vx, Vy plot. It is no longer an ellipse, it is lying on a straight line. Okay, the other two views are still ellipse. It is an ellipse. If this were an ellipsoid, in this view also we would get an ellipse. Okay, so the linear velocity ellipse at a last singular point degenerates to a line. Okay, let's continue and look at this 3 RPS parallel manipulator and look at the possibility of gain singularity. Okay, so as mentioned, this 3 RPS parallel manipulator will gain one or more degrees of freedom when determinant of K star equal to 0. Okay, so I have shown you what the K star matrix was, and I can compute the determinant of the K star, and it will be a long expression. Okay, so it is one product plus another product. So, and it contains L1, L2, L3. These are the actuated joint variables, and theta 1, theta 2, theta 3 using sines and cosines, okay, in both these terms. So the determinant of K star equal to 0 is a function of all the 3 thetas and the 3 phis. So in this case, phis are the thetas. The passive joint variables are thetas, and the actuated joint thetas are L1, L2, L3. Okay. So determinant of K star is an expression involving all these Q's, all the actuated and passive joint variables. Okay, we also have 3 loop closure constraint equations. Remember, the distance between the 2 spherical joints is given and pairwise. So we have 3 equations there. And this together will give 4 equations in 6 unknowns. What are the 6 unknowns? L1, L2, L3, theta 1, theta 2, theta 3. So conceptually, it's 4 equation in 6 variables, which basically means it's a 2D surface. Okay, but it is very difficult to eliminate and get analytical expression of this surface where the determinant of K star is equal to 0 and where the 3 RPS manipulator is gaining degrees of 1 degree of freedom. Okay, let's do numerically. So for L1, L2, L3 given by 0.575, 0.483 and 0.544, we can solve for theta 1, theta 2, theta 3, and we get these values minus 0.34, minus 0.138, 0.2320 radians. Okay, and you can show that this determinant of K star is approximately equal to 0, very close to 0, because this is a numerical approach. Okay, so when we solve for the direct kinematics, it will never be exactly equal to 0, but okay, this is like 10 to the power minus 5. The 3 eigenvalues of K star are approximately minus 0.5565, very close to 0, and 0.4509. And the corresponding eigenvectors for minus 0.5565, 0, and this are given by this. So, which is the direction in which the 3 RPS manipulator has gained a degree of freedom? It corresponds to the eigenvector for the 0 eigenvalue. Okay, so and the gained velocity of the centroid is given by this vector into theta 1 dot, this vector into theta 2 dot, and this vector into theta 3 dot. Okay. Okay, so this 0.31098743 and minus 3727 is the eigenvector corresponding to the 0 eigenvalue. So alpha times that is also an eigenvector, and that is what has been used here. And when you substitute that in the linear velocity vector, you will get these actual theta as a function of theta 1 dot, theta 2 dot, and theta 3 dot. Okay, so it has gained a degree of freedom. We can also now plot what is this velocity vector which it has gained in 3D plot, XYZ plot. You can see that it moves along, it can move along this direction. In the Vx, Vy section view, the gained velocity vector is along this direction. In Vz, Vx, it is along this direction, and Vz, Vy, it is along this direction. So the end effector can move in this direction. Let's continue. This 3RPS is a simple manipulator. We can do more work with it. So at L1, L2, L3 given by these values 1.9363, 2.9998, 1.9363 meters, the corresponding theta 1, theta 2, theta 3 are given by this. Okay. And it turns out determinant of K star is also very close to 0. So how did we find these numbers? L1, L2, L3, we just do a search. Okay, same story in the previous case when we lost 1 degree of freedom. Okay, so when we gained 1 degree of freedom. In this case, the eigenvalues are 0, 0, 3.9680. So there are 2 0 eigenvalues. So which means what? It has gained 2 degrees of freedom. So the singularities correspond to the gain of 2 degree of freedom lie on a curve. The singularity corresponding to gain of 1 degree of freedom lies on a 2D surface. So we have one more equation, so hence it will lie on a curve. Again, it is very difficult to get analytical expression for that curve, but we can again plot it. So we can plot the gained degree of freedom, and you can see in both in the 3D plot as well as in the sectional plots, we get ellipses. Okay, so the tip of the linear velocity vector lies on an ellipse in 3D space and also in the 3 sectional views. So in summary, the singularity in serial manipulators leads to a loss of rank of the manipulator Jacobian. It also implies loss of 1 or more degrees of freedom. Geometrically, the velocity ellipsoid or ellipse degenerates. So ellipsoid will become ellipse and ellipse might become a line. It is not possible to move along the singular direction. So what is the singular direction? It is perpendicular to the direction of motion. The singularity in parallel manipulator, you can also lose 1 or more degrees of freedom, very similar to the loss of degree of freedom as in a serial robot. But it can also gain 1 or more degrees of freedom with actuators locked. Okay, so the gain of degree of freedom is due to the loss of rank of K star and determinant of K star equal to 0. So I showed you examples of planar 2R and a 3RPS parallel manipulator. Okay, so with this we come to an end of this discussion on singularities in serial and parallel manipulators. In the next lecture, we'll look at the statics of serial and parallel manipulators.